Hello.
Good afternoon, sir.
Right. So without further delay, I will simply start a 15-minute, quick work in AutoCAD. Alright, from 6 o'clock the resource person will join. So actually I wanted to show you the surface modeling part in AutoCAD, how it's done. Alright, so for that let's draw two splines initially like that. Okay, this is say the first line and this is say the second spline. Okay, like this. Okay, it has become like this. So I want to connect these two again. So what I'll do, realistic, then this, and maybe I will move it. Yeah, I will move it. I have to move. Okay, to move it. It's not realistic. Say 10. All right. Now this way. Let me connect this two. Let me take this. Just ensuring that the extreme points are the ones to be connected. So from here, the extreme point. Alright. No, it's not. Okay. Another copy of this from here to here. Then I have to revise this. Okay. Alright. So this is a surface in 3 dimension, as you can see here. Suppose you have to design a surface like this, then what you have to do, you have to simply click on surface, then network, then it asks for the select curves on surface edges in the first direction. So in this direction or in this direction, whatever the direction you take, in one direction only you have to select two curve or straight line, whatever. So in first let's select in this directions only, these two, then I have to select enter, then again this one and this one. So this is the second direction, then enter. Okay, so you see one surface has been generated. Now this surface will not get printed, so I have to thicken. So click and let's write say 4. Okay, so you see a thickness of 4 has been given. So this is a surface. The surface has been generated with a thickness of 4 mm. All right, so this is one way. This is one way of generating surface. Suppose you have to design something by your own judgment. You may not have the exact dimensions and the bounding curves in all the cases. So in that case, what you have to do, okay, so in that case, suppose say this is the surface. So I, or let it be like this. I want to directly, I can create one plane here. So this will be my reference plane. Okay, this is my reference plane. Now in this reference plane, what I need to do, I need to adjust these points. Okay, I need to like move one point relative to other points, so that it creates a curve sort of thing. Okay, so in that case I have to first convert this NURBS. So you have to select all these things, then enter. Okay, so all this entire grid has been converted to some points which can be moved by pulling it or pressing it. Now where are those points? You will not be able to see those points until you select show CV. So then if you select here, you can see only 4. This 1 2 3 4. That means by you can move these things. You can see you can move these things, isn't it? But you need more points here, okay, in between, so that you can play with the curvy face. Okay, so for that you have to click on rebuild. So click on rebuild, and if you click here, it will ask for like how many counts. Automatically it will like generate some numbers in the x direction and y direction. That means a matrix will be formed. So you can like reduce or increase those numbers. Let's go with the default value. So you see these points have been created. Now you see these are the points. Okay, so already this surface was moved like this. So you can still by selecting here, you can make it like this. You can like make it go like this, or maybe this point can be so you can play in whatever the directions you want. You can play. So after playing, you of course don't want this blue dots to remain there, so you can simply hide. Okay, you can simply hide, and then of course you can thicken this as well. So select thickness, so let's give 2, and let's go to here and realistic, and see, let's see. You can see a thickness. So any kind of irregular planes, because this particular, you might have faced the absence of this tool while modeling your objects. So I felt like quickly let's take a class of 15 minutes before the resource person arrives and learn how it's done, how the surfaces are done. Okay, and apart, see, AutoCAD is a thing that cannot be taught in 2 or 3 classes. Okay, this is something like diploma. You have to learn AutoCAD by enrolling for say 30 days or 20 days, sometimes even 6-month course. So many things are left out. One of the things, like say there is a box. Okay, there is a box. So in this box, if you want to create something like say this is a box, but this is used for say putting something. That means it's like a pot. So you have to again draw one smaller square at the top surface and then press pull it, or you have another option called cell. So you can go here, you can select on cell, right click the cell and the surface here, then it will ask for offset distance. That means the thickness. So thickness say 2 again here. So you will see here, if you go a box has been created. Here the thickness will be 2, and all the thickness, the entire thickness will be 2, and since I selected the top surface, so the top surface has been removed. Okay, you could have selected this surface as well, this surface as well, any of the surface. Okay, and similarly you can find out, you can play with this other options, the slice. So if you select on slice, okay, the slice has been selected, specify the first point, so from here to say here it has been sliced. Sometimes you may require only one part of the object, the second part can be removed. Okay, so like that. I know I couldn't justify teaching you 3D in detail, but it's okay if you know how to at least extract and extrude and press pull, the basic commands revolve, then sweep and rotate and move gizmo, then you can create any of the figures. It will be a little bit longer than the actual time. Because of the shortcut, you may reduce the time of constructing the model, but after knowing these things, you will be able to draw, you should be able to draw any kind of object. You will not feel like a handicapped person. Alright, you will not feel that. Maybe the time can be a constraint, maybe your patience can be a constraint, but your knowledge will never be a constraint if you want to draw, if you want to model any kind of object. And another constraint can be the dimensions, the lack of dimensions. Alright. Okay. So most of you have joined. Let's wait. We'll be joining shortly. And by the way, your tomorrow's visit has been cancelled. Not cancelled, it has been postponed because of the emergency of the resource person. Will not be available in the lab till Monday. So the next date that has been scheduled is Tuesday. So Tuesday, it can be at any time. You will let us know, but Tuesday you please keep yourselves free from other duties, other commitments, and hopefully we will be meeting near ABC, near the Donna planet. Let's assemble at Donna planet, near in front of the gate of the Donna planet at whatever time he says on Tuesday. Then we can move to his laboratory, and 2 hours we will be spending there. Okay, I think the resource person has joined. Juan.
Hello.
Yes.
Hello everyone. Yeah.
Yes. Okay, so Juan has agreed to come and share his experience in 3D printing. Many of you already know him. He has been a faculty in Assam Engineering College for the last 3 years. So still, let me introduce him for the ones who don't know. He is a mechanical engineering graduate from Guwahati University and has a master degree in computer assisted manufacturing from IIT Guwahati. His research domain comprises electromagnetics, actuators, and nonlinear control. He is trained in several soft skills, including CAD, and his professional experiences include 3 years of service as a faculty in Assam Engineering College, 3 months as assistant project engineer at Scientific and Engineering Research Board IIT Guwahati, and 9 months as project engineer at TDPCM Amingao. So thank you, Juan, and welcome to the workshop. The platform is yours.
Thank you for this kind introduction. I hope you all are enjoying, and my fellow colleague, now of course a teacher to me now, has been teaching you really well. So I want to give you some nuances of 3D printing in certain specific areas. Let me talk few minutes about what I would have come across in this all this time as an engagement with 3D printing. So because my domain is from mechanical engineering, I was trained in how, as in general, manufacturing processes undergo, not necessarily additive. This is pretty recent, additive manufacturing. Uh, it was all about subtractive manufacturing. So back in the day when I was a student, it was all about subtractive manufacturing, where we would use lathe machine, shaper machine, milling machine, drill machine, and whatnot to remove a certain block of material. Now things have changed. We are moving into additive manufacturing, and coincidentally, that also happens to be my research area. However, I have also explored certain domains where I started off learning how a 3D printer is built in general. What sort of elements do we require? Talking about motors, talking about sensors, actuators, control logic, okay, communication protocols, things like that. However, I feel you, of course, in which you are already trained, as I can see from the group messages, I have a certain inclination towards CAD modeling with respect to, of course, mechanical engineering components. I believe most of you are from civil engineering background, and that should not be any reason that you should be holding back your creativity. Okay, being an engineer, you're just open to learn anything. Before I begin and put myself on, the pedal, I want to know if you have any fundamental questions. I want to know if you know what FDM 3D printer is. You can use the chat box. Yes, no. Be very kind. At least I would know that I'm audible and things like that. Are you familiar with FDM based 3D printers?
Participants?
Right. Okay. Great. Great. Yes. Fuse deposition modeling. Okay. So that is not right. So that is not the only type. As you will learn in continuation, we have several other methods and several other physical backdrops through which 3D printing is possible. What I work on is eventually high-speed 3D printing. So that takes the 3D printing time to a very low very high rate of production. Okay, so that is my field of scope. So I have a couple of stuff which I want to discuss, but perhaps I will start off by teaching you a bit of CAD modeling in SolidWorks. So as such, you are already familiar with AutoCAD. There's not much difference between the two. It's just that for AutoCAD, it is really good for planning architecture and large scale layouts. However, for SolidWorks, it is more equipped to be functional with machineries, components, okay, and then further as you would learn how assembly simulation can be carried out. How is it anyway relevant to 3D printing? Because when you start building any part, There is as such no backdrop to what software you may use, but it is of course advisable to use plenty of softwares, as different systems might have different integrable components. One of the systems based upon stereolithography is housed in Assam Engineering College in the Mechanical Engineering department, is one of the latest technologies which is commercially available. Even in that, maybe you would want to know a bit of SolidWorks. So I just want to know if anybody is uh, already familiar with SolidWorks. Just yes and no, that will be good for me. I'll pace up accordingly. Is anyone familiar with SolidWorks?
No, sir.
Okay, no problem, no problem. All right. So I'll just go a bit slow, and maybe I'll show you the features so that you can expand your imagination. And later, if you wish to join, of course, plenty of tutorials are available in YouTube, and they are pretty good also. Okay. So let me just start off with two parts of SolidWorks, and then maybe I'll just go in depth on how SLA technology is used for 3D printing process. Okay. So I'll share my screen over here. Okay. Yeah, can you see the screen? I would need a voice cue because otherwise I cannot see the chat box. Can you see the SolidWorks 2019 screen?
Yes, sir. Yes,
Yes.
sir.
Also, one good fact about SolidWorks is that the full free trial is available online in solidworks.com. You can get it for free if you register it there as a student. Okay, that's free of cost. I believe the trial is for 15 or 30 days odd, something like that. Okay, so you can very well utilize it. Also, SolidWorks comes with a lot of direct extensions, by which I mean, say if you have heard of some software called ANSYS or Abacus, COMSOL, things like that, it has a direct connection, which means that it will directly import parts. Okay, you don't have to save it in other format and then bring out the module. Or then there's some interchangeable parts also. You can use some models from other softwares and incorporate it in your own. I believe it is also integrable with MATLAB. Okay, so the layout is pretty simple. The graphic user interface is very good. One alternative I would suggest to SolidWorks is CATIA. Again, it's a very standard industry-based modeling software. Okay, so in this particular menu, you will see there's something called as a home button. Okay, then new file, open file. All right, save, print, and undo options are not available as of now because we did not start. A similar set of options are available over here: SolidWorks resources, design library, where you can bring out parts. By default, you don't have to design them. There are standardized parts. File Explorer, if you want to import any within your system. There are different palettes if you want multi-view of any component. And then you can design appearances as per your liking. That is, I believe, available in AutoCAD also. Okay, you will not feel much of a difference except for the fact that I believe the graphics is a little refined. So as I click on new, it asks for if you want a part assembly or a 2D drawing. Okay, you can also lean into some advanced systems like this. Okay, some pre-defined assembly parts and some tutorials which are available as per the requirement. Okay, so in the templates, I'll start off with a part, click on OK. All right, so there it is, an overall backdrop on how you should start. So just like you select some planes in AutoCAD, the same thing exists. It's just that it is conveniently placed on the left side, the one that is front plane, top plane, and right plane. Okay, then the origin, which is the global origin, is mentioned over here. And just below that, you can see there's something written as trimetric. So this is the view through which you are looking at the object. You can change it to anything you like from these buttons, from orientation buttons. As you see, these cubes are available, and then you can easily select whichever view you like. Okay, as I'll start to begin to model some stuff, you'll realize these views are pretty convenient on how to use. And then if you are not very fond of some background, or you want some fancy background, a lot of things are available over here, okay, to put your product, just to give it a very realistic perspective. All right, things like this. I go with the generic one. All right, so let's start with some simple elements which you already know. I'll start off drawing in the front plane, okay, to make it convenient. When I click on the front plane, there's something called a sketch, show, zoom to selection, and normal to. Okay, if I click on zoom to selection, it'll zoom. Simple. If I click on show, it'll show. If I click on normal to, it takes me to a normal frame, all right, on which I'm looking from the front view. It is of course very convenient to do so. Now after I have done this, normal to, I'll go to sketch, and you see a plenty of options which are available over here, just to start off with a sketch. Now I feel, because I am told that most of you are from civil engineering background, let's try to build a manipulator. But what we will do is not build it as a whole, but build it part-wise. Okay, what's the use of building part-wise? Then we also get to learn how to assemble them together. So I'll just think of a schematic and then straight away model, maybe not put much dimensions into consideration. So let me give you the schematic. I'll start off with paint. I believe I need to just switch my screen, just a second. Right. Okay. So as you see over here, I've opened a simple paint, and say you want to build up a pick and place robot, which is conveniently used in very high performance civil engineering applications, which also involves robotics. Okay, so it will have a base frame. Okay, and the base frame will be somehow mounted on this platform. The base frame can rotate, okay, by theta angle, say for example, and then I'll have an arm on top of it, okay, and a second arm, all right, and a simple C-shape gripper, okay, just pick and place. So how many degrees of freedom do I have over here? That's 1. The rotation is possible over here, that's 2. Theta 1, 2, and 3, okay, theta 3. So just with this thought, I believe I'll start modeling the system, and maybe how realistically I can build the system. So what I'll do, I'll not just model it throughout. What I'll do is, because I want relative motion in between, I will start modeling part-wise. Say this is part number 1, part number 2, part number 3, part number 4, and we'll think about the end effector later, okay, the gripper later. All right, so what's my notion? Because I'm modeling each part differently, now when I'll put it in the 3D printer, the time consumed for each part will be lesser as to if I would have printed it in one go. Okay, so because of power constraints, material constraints, you have to keep this into consideration, that once you have started the print, if you stop in between, there's no going back. Okay, you just cannot stop and then restart over the place again. The part gets destroyed in most of the cases until it has a specific mechanism to revert the process. So what we would like to do is start building part-wise, and then we'll see how the time consumption will be lesser, and then rather than assemble the parts conveniently. Okay, so that's my idea. I'll go to SolidWorks. Right now, because I'll start with the base frame, the frame number 1, let me start with the top plane. Okay, so I'm looking at from the top. So I'll go to a round base, which essentially means a circle. Simply draw a circle and then make a small hole on top of it. Okay, and that we can conveniently dimension it also. So say I want the base to be around 30 centimeters long. So I can simply type 30 centimeter. Oh, by the way, sorry, if I move really fast, let me just, so there's a feature called smart dimension. So the object that you click, it automatically picks up if it is a circle or a line or a square, and then it tries to match the dimension as you enter. Okay, the size of the object accordingly changes. So if I click on smart dimension on the left top of the screen, I click on the outer circle, and then I'll just type it as 30 centimeter. Right, that's a 30 centimeter. There's this, I believe this feature is good because the inner circle, we did not dimension it earlier, so the relative dimensioning has taken place. Okay, the larger circle did not surpass the smaller circle. I believe this is a good feature of SolidWorks. So keeping the smart dimension on, I'll click on the smaller circle and give it only say 5 centimeter of radius because I want it to have a hole in between. All right, this is an exit sketch button on the right, the blue one. Okay, there's a cross. If I click on the cross, the whole sketch will get cancelled. So it just asks me, if I click on the cross, that do you want to discard the changes? If I do so, the entire sketch will be erased. Okay, so I'll just skip out of the sketcher, and you see two small lines that have taken place. Now it might seem a little inconvenient that I have not laid out any grid and something like that. In most cases, we do not lay out any grid, okay, because the dimensioning feature is really flexible in this system. All right. So because I have created two circles, of course, you would know from AutoCAD that you can extrude it to form a small disk, isn't it? So this time around, we'll move from sketch of the object to features. Okay, I'll go to feature. I'll click on extrude base. Now I have clicked on the outer circle, if you have realized. Okay, what it is doing is it has created a disk without the hole. Okay, the disk is without the hole. So here, if you see selected contours, you can select this contour and right click over there, and what you can do is clear the selections, remove what is being extruded, and then simply select the profile. Okay, now as I increase the height, okay, it can be done with that arrow. You can type it around, or also you can pull. All right, you can pull in both directions. All right, so let's not keep it that way. It says at 85. Okay, it feels fine at 85, looks particularly stable, and there you go, there's the first disk. Okay, just try to remember the part of it. Okay, it was 5 centimeter hole and a 30 centimeter base. So this is our first part. What we can do is, as we are modeling it, we can straight away put to print. Okay, that is a very good feature of your, you can directly connect it to the printer and put to print. Okay, so I'll try to save it. Okay, it says part 2, that's fine. Yeah, so let's start off with another one. Go to new, select on part. Now this time I want to build the arm. So part 1 is done. Part 2, the triangular arm, okay, which should sit over a desktop so that it can rotate. That's the idea. All right, so part number 2 we are about to build. Let's go to the front plane. Right now, in this front plane, I'll start off with some, now not circles and anything, with some random sketches. Okay, I'll show you why did I do that. There's a line function over here. Okay, you start off with line, and it's always convenient if you start from the origin, which it will automatically snap onto. Okay, just draw it. Very random. And what I want to show you is that you need not keep a thought about the dimensions as you draw, because the smart dimension feature will take care of it. So right away, I can click here and just tell that this is 15 centimeters long. This is 5 centimeters in height. That's again 5 centimeters in height. Right? And then I can set the angle now. All right. How? Just click on the line, keep the smart dimension on, click on the bottom line, and as you can see, it says that it's at 67 degrees Celsius. So let me just set it at 60 degrees Celsius. Do the same thing, click on the line, click on the bottom line, set at 60 degrees Celsius. Sorry, not Celsius, my bad. Yeah. So the top dimension is automatically deduced. I can keep it at 40. Okay. So that's the arm, which is done. Couple of things that I should keep in mind. I would need a hole for the robotic arm to be ready. Okay. But yeah, that needs to be there. So I'll just switch to a circle. And as I'm moving throughout the sketch, you will see that the pointer always snaps to the center. And if you start to pull down, it will always stick on the center line. All right. That's a very good feature. And I'll somewhere in between, I'll just randomly draw a circle and then say that let this be 5 centimeter of diameter. Okay. Now I obviously know this is centered pretty well, but I want to also put restriction on the height. So I'll select the line from the top within the sphere and 40 mm. So that's done. So like the old times, our sketches are ready. Okay. Maybe I can also, show some filleting features. Say we do not need such sharp ends. We need some smoother ends. So there's something called as fillets here. Sketch fillet. Fillet and chamfer. I believe you know the difference between the two. Fillet is a round curvature that will be made. Chamfer is a horizontal line by which the edge will be cut down. Okay, we'll do both and let's see. Sketch fillet. So what I need to do is just simply click on the corner. Okay, and as you can see, it has already set by default how the shape will look like, and maybe I can change it to even more, rather less, 5 mm. If I click on it, there's some nice beautiful round edges. Okay, and then the chamfer one. All right, I'll switch to chamfer. Click on this edge, click on this edge. So can you see the straight lines? And then what you have are some corners. So that's the difference between fillet and chamfer. Yeah. Now I can pull out of the sketch. Okay, my body is done. What I need to do now is extrude. Right. So click on it. Again, it did not select the whole profile. So we will right click on it, clear the selections. It automatically selects the system. Set the thickness 10 mm. That's fine with me. Not a problem. So there you go. Another part is being made. Okay. Now, of course, if you conceptualize that only one arm will not be sufficient, we would need a fork-like thing. Okay, so a very convenient feature is something we call as mirror that you use. It can be done to solid parts also. Okay, so what I'll do is introduce something, a reference in between, and then do the same exercise, okay, of mirroring. Let's see how to do it. Okay, so as you see, I drew everything on the top plane, and the top plane is on the interior of the body. Okay, if I'm looking from this perspective angle, it is towards the interior of the body. So what I can do is make a plane in between and take the plane as reference and mirror the component. So I'll have the two fingers of the fork. Okay, let's try to do that. Plane. All right. Oh, sorry. Let's go to reference over here. Go to plane. Okay, and you can select the face also, not a problem. So as you can see, automatically it has made a plane out of it. Okay, and then you can set by what amount of distance do you need the plane. I want it 5 centimeter apart. Okay, that's done. So my plane is done. Now what I want to do is create an exact copy, just a mirror copy to this particular body. Okay, what I'll do, I'll go to mirror. I need to find where mirror is. Yeah, right in between linear pattern, there's something called as mirror command. Once I have selected the mirror command, it says mirror face plane. I don't want to mirror any faces. I want to mirror a solid body. Okay, so here you can click it, bodies to mirror. So that's a whole body that will be mirrored. And then you can select by what uh, index do you want to mirror. Again, simply click on this, and there you go. Oh, sorry. Right. So there was an error. I think I should take you back to the error. That's where the concept is. Right. Let me do the process. Go to linear pattern, click on mirror, and then go to bodies to mirror, select the body. As you will see here, there's something called as merge solids, which means that any part, any geometry that you will make on top of this part will be counted as one single part, one solid object. Okay. Now, because this option is selected and I have mirrored this particular object about the plane, okay, merge solid is on, which is practically impossible. These two objects cannot be one solid because they are not connected by any element. Okay, so there we will pull off this option. Okay, and if you click on it, the two objects will be made. So if you remember, I was talking about an option which you can hide it, show hide plane. So if you right click on it, the same 4 options will appear, and here you can click on hide. So that's gone. Okay, now one would not know that this is being mirrored. Okay, the best part about making a mirror is that any changes, further changes that I'll make to this particular object will be reflected on the opposite mirror also. Okay, you can give it a try in your free time. Okay, now finally what I need is a base plate at the bottom, which I could have done it earlier also, but I can do it now, not a problem. In SolidWorks I can draw a base plate over here and then make a cylinder so that it fits right into the object. All right, okay. For this you can make another plane, you can select the top plane, and a very convenient feature with SolidWorks is that I can right away click on this plane and start drawing here. Click normal to, and it will allow me to draw in that particular plane. Okay, I don't have to worry about making a new plane or selecting the right plane. Okay, it automatically understands that this is the plane that I want to draw. Go to sketch, make a rectangle. I'll select edge to edge. Should be convenient for me, right? And there again, simply go to features and make a base plate. Now here you will see there's something called as merge result, and exactly what it is, it will merge the results, which means now all these bodies will be considered as one. Very important when you're talking with context, in context to 3D printing, because there should be a continuity of elements. If there is a break in between, the continuity gets missed and you will have some aberrations while printing which you were not predicting while modeling the part. Okay, now the base plate is done, the fork is done. All I want to do is at the center I need a 5 centimeter cylinder which should right away fit in. Okay, I'll go to the bottom surface again because it is convenient. Go to sketch, select a circle, and as you remember, I can snap, right? I can snap to the edge of the body. Snap means it is directly selecting the midpoint. Okay, bring towards the midpoint, and it should also give me a midpoint from the side edge. Right, there you go. So if you remember, the whole size was 5 centimeters. I'll put it that way. Okay, and then give it an extrude of 60 mm. All right, this should be all right now. Okay, there you are. We have the fork, okay, for the robot. I'll save the same part as part 3, minimize it. Now let's already begin to assemble. Why wait for such time? Let's start to assemble. So what I'll do is go to new. This time I'll click on assembly. Okay, and by default it understands that part 2 and part 3 are already made recently, and I should be able to put these parts down separately. Okay, part 3, as you can see over here, two different parts. I can move it anywhere in the plane. Okay. Now the interesting parts come along. What I want to do is put this cylindrical object into this cylindrical hole. Okay. And as I do that, I should also have the flexibility of a rotating motion, isn't it? I don't want to fix it in a particular assembly. So what I'll do is I'll just click on mate. In this mate selection, you can select the cylinder, this particular cylinder, and it automatically aligns. Then select this surface and the bottom surface, so it will fit down. Now I would wonder that does it have the flexibility or not? So you can just give it a rotation and see that yes, it absolutely rotates about the axis it has been asked to. Okay, this is a flexibility with SolidWorks where you can assemble things and also generate relative motion. So right here, I would like to give a little pause and ask you if you are able to follow. I don't want you to do exactly what I'm doing, but are you able to follow how SolidWorks works? At least yes, no, in the chat box.
Juan, I have a doubt.
Yeah.
Rotating these two assembles, these two parts in SolidWorks is okay, but when they get printed, the size will be like almost, it will be exactly same, 5 centimeter, 5 centimeter. So will they get rotated in real life also after getting printed?
Yes, exactly. That is something I was about to talk on. When we are doing an assembly and then we are trying to 3D print an object with the modern technologies of SLA, SLS, where you are printing assemblies altogether, not parts, then you can have this motion as well in the system. You will have this flexibility where after printing, if you remove some structures in and around it, it will absolutely give you the required motion that you were seeking for. Yeah, just I would like to know from participants, is it all right? Or am I moving really fast? I should slow down a bit. Anyway, these sessions are recorded. You can go and have a look later, but I want some feedback so that I know, okay, what to do. All right. Akash says it's fine. Anybody? Okay. Thanks to him. All right. We have already begun to assemble. All right. So I think this is a good pace we are moving now. People are getting it. Right. So 2 parts done. You can of course imagine how the third part can be manufactured. I'll show you an example how to fix parts now again. Okay. Now this also always gives me a lot of flexibility, considering the fact that when in my experience, when we have 3D printed several parts, there's always some amount of design iteration we would like to make. Okay, so it is always advisable that you make 2 parts, one with the utmost design interventions that you would want, and one with the most stable design without actually manipulating a lot of systems. Okay, so for that, in this particular context, I'll now proceed in making the arm of the crane in the robotic manipulator, which we need to 3D print. Again, go to new file, go to part, front plane, normal to, same process, go to sketch. Now in sketch, there's a very convenient option called straight slot. Okay, this actually allows a lot of quick design, as the slots are most likely used, as you will see. So as you can see, I have drawn a line, and then I get to decide the radius. All right, these are all in proportions which you can manipulate. A simple structure has been done. Otherwise, I would have to make a rectangle, make a semicircle, trim the rectangle sides, and the solid object would have been done. Okay. There are different types of slots. Okay, things like this. If you wish, well, I'm not going to use then obviously, just to give you a demonstration on how it works. Okay, right. So let me make this arm length at around say 40 centimeters, right? And this edge height as uh, say 100. 1/4 will be too high. 80 centimeters. 80 will be too high. Centimeters. Oh, sorry. Centimeter. Okay. 5. 10 centimeter. Right. Yeah, this better. Let's take 50 centimeter. Pretty long. Then what I'll do, I'll simply click on make these circles and make them 5 centimeter in dia. Okay, 5 centimeter in dia. Exit the sketch, go to features, extrude, select the profile, clear selections, give a thickness of 20 mm, 2 centimeters, that's fine. Okay, now I have a one part of the arm. This is not the entire arm, that's just one part, and that's all actually I require. What additionally what I can do is on this particular face, I can make some square objects just as a support. Okay, so set it at 400 mm, height at 20 mm, and displacement at 30 mm. Most probably I could not. Right. Okay, I'll go to features and then take it to 25. Say the distance is 5 centimeters, right? So 5 centimeters should be fine. Okay. So that's one part. I'll save it as part number 4. All right. And immediately when I move to assembly, insert components, part 4 will be available for me. Okay. Now, as you see, I have put it in any random orientation, but that's not a problem. I'll just align it with the system. Put it on the inside, right? There you go, a perfect alignment. Again, the question, can I move it? Is it a fixed assembly? No, of course. I can move this arm, all right? So in SolidWorks, there's a feature of kinematic assembly also. And again, this part can also be moved, okay? So if you remember, I was talking about the fact that I would really want only one part to be made. So if I 3D print this arm twice, I'm going to get the exact same thing, isn't it? So right away, I can assemble them and they'll form one single arm. Let's just rotate the component a little so that we have perfect orientation, right? I'll click on this and make them again. And then eventually I'll pull the system. There's a tad bit of overlap because of rotation. Now what I can do is give this to a coincidence. And as you see, they have become a one single arm. Of course, there's an overlap. If I change the dimension, okay, in real time, this overlap will be gone. Perhaps I'm off by around 1 centimeter. So let me take it to 2 centimeters each. Again, I do not have dimensions in mind, hence this problem. You would not face any problem of this sort. So as I do save it, it'll ask me if I should save in the assembly also. Yes. And it should be reflected. Oh, Okay. I think the SolidWorks just paused for a while. It will be back. Yeah. Okay. 2.5 was even little less. So a bit of iteration, and then we are good to go. Now this link will move together because they are fixed. And the best part is that you don't need to print the whole link together. You can, of course, make such arrangements. Okay. Put a cylinder in between. This particular robotic arm is done. Okay. And then, of course, what I can do is, instead of making another arm, I can just import two different links and then make another arm of over here. Right, this seems to work well. Okay. And I have to rotate this component. Okay, let me show you this particular case where there might be a problem. See, if I made in this particular orientation between these two holes, now the protrusion actually went outside. Do you see that? I wanted a flip of it. Okay, I wanted this within its axis. So hence I have been rotating the element over and over again. So let me delete this part. In here, left hand the tree, you will quickly see that there's a concentric mate. I have not been very delineating about the definitions of it, but making most out of what I know of SolidWorks in this short time. Okay, so what I'll do is I'll rotate the component. Okay. Now, rotate in any direction doesn't matter. It's automatically going to align itself. Okay. And then a parallel constraint between these two arms. Right. There it is. Your crane is ready. In those cylinders will go the motors, the shaft and everything. And over here, then I can, manipulate this arm. All right. Okay. All right. So it is this convenience of SolidWorks for which I prefer modeling. Okay. Right. So now what you can do is, again, give it a perspective projection. All right. As I'll zoom in, you will see the difference between this perspective and switch off the perspective. It looks like this. Switch on the perspective. It gives a more real feel with shadows and everything. Okay. You can make any changes in this part. It will automatically be reflected in this assembly model. All right. Now, let me quickly switch to drawing now. I'll save this as assembly 1. Okay. So the third part of this assembly, of course, these are not the only systems that you make. Say you want to make 100 robots out of it, you can as well. All right. Right. So this is how you can go for large scale systems. See, n number of robots. All right, all moving coherently. This is one thing you can do. Also, I'll just undo it. Okay. Circular pattern. Let me show you this too. I'm not sure if I will be able to give it a pattern. The direction. Yeah. So if I had an axis away from the system, I would have been able to, make multiples of robots over here. But of course, you can make such arrangements. Okay, make complex parts, build in one assembly, and then iterate the assemblies to make one single component. Okay, you can 3D print it. All right, so these are some of the features of SolidWorks. Let's take you to how assemblies are then converted into drawings, which we usually do. Now, the only reason I did not start with any dimensions because I wanted to show you how the dimensioning takes place. I'll take you to make drawing from part assembly. All right, instead of new, this time I'm going to take to make drawing from part assembly. Okay, templates drawing one. You start off with selecting the size of sheet. Okay, A4, A5, B, C, D, whatever you want. Okay, landscape, right. So right away on your right half of the plane, you will see all the front view, top view, right view are available. Okay, that's based upon the orientation we have kept it. This can be changed also. All right, and what you can go after is here in sketches, you can again find smart dimension and then put all the dimensions as per requirement. Okay, we don't have to consider dimensioning it again. These are of course in a tilted view. Let me change it rather, otherwise it will create some problem. Okay, yeah, okay, let's check it out now. Make drawing from part assembly, select a paper. Okay, come up with front, side, isometric top, and isometric view. Okay, we can select a larger paper if we want. Now here we can go to sketch dimensions and you can put away exactly what the dimensions are. Okay, you can see whatever we have put, all the diameters, holes, etc., everything is available. So that's a quick introduction about SolidWorks. Made it quick because I did not want to, spend more time teaching you a new software after you have mastered one. But this kind of shows how flexible SolidWorks is. And if you want to build systems which can simulate, this is a very good option. Okay. Any questions? Not in particular to SolidWorks, but anything to solid modeling. Okay. Do you want me to explain any part? I'll be happy to do so. Anything?
Sir, sir, is there any restrictions in printing the movable parts? Like, can we print anything like screws in one model as well, like hinges?
Absolutely. Yeah, absolutely. There's no restrictions in printing part, and perhaps that's a very good benefit. Let me, I'll just give you on this particular note. I'll show you one thing. I'll save this drawing too. Okay, and move back to assembly. Right. So as you were talking about screws and everything, let's say the system that I want to build should have screws and stuff inbuilt over it. Okay. So here is something called as the design library toolbox. Okay, this is not added. I'm not sure if it will work or not. Perhaps it won't work. Right. So as you can see, if I pull this flange bolt, I can select what dimensions do I need. All right, over here. Let's go to M16, which will be a larger version. So I can put multiple of them. Okay, and then assemble them. I'll come to your questions precisely. not the right dimension, but it should work in proving the concept that I wanted to deliver. So example, these are the screws, okay, and the rest we can delete them. Don't need this. Right, so imagine these are the screws that you have put and these are suspended. Okay, I'll save it. Now here I'll save it as, instead of assembly, I'll just click on STL. Okay, and as you can see, the whole body STL is created. Let me try to open it. And I believe you saw a little picture of how STL has been found. Let me just try to save it again. So I hope you can see this, the STL file being created of the entire object, which will be by default built as an assembly, which you can move. Now the screws, if you remember, I have put it in between, right? So there's nothing that's holding the screws in place. So while printing, it's exactly going to print it that way. Just it'll create some words for the structure to be printed, and later which you can remove and still get the assembly rotating. All right, is this part clear then? Is the doubt resolved?
Yes, sir.
Okay, great.
Thank you, sir.
Anything else? So in SolidWorks library, there are actually plenty of stuff that you can do, which are inbuilt, and rather more than inbuilt, why I preferred them is because they are standardized. Okay. You can find these type of surfaces, curvilinear surfaces, which are by default made. Okay, so you don't have to put your head to this to generate this complex surface textures. I believe this is a good feature that SolidWorks provides. Again, yeah, you can put some decals over here. You know, say I want it. Just a second. So say I want this to be chrome metal, right? So while rendering, all these objects will be created with chrome. Okay, these are the decals that you can put. These are of course superficial in nature, doesn't really add up to the printing quality in general. Okay, so if you want to learn SolidWorks, there's a by default SolidWorks channel that's called CAD-CAM. You can go ahead with that. It's quite extensive, but what I understand from it is that the flexibility is very high on top of it. So that was not all, but some on SolidWorks. If you want to go ahead and do some stuff, you can of course come back to me. All right, I'll just share my mail ID. If you have any doubt regarding it, you can go ahead. Okay. Also, you can download SolidWorks from this link. And then again, the mechanical engineering department in the AC has a license for SolidWorks, which you can get it from. Link or download for student versions. Okay, right. So in the next part of the lecture, maybe I'll start off with delivering about the components of SLA machine. Okay, that way maybe we'll build up a little bit of intuition on what is to come in our consecutive classes. Okay, so what I'll do is I'll start off with some elements. I have a couple of presentation, but probably the best way to learn is, write everything down. Okay, let me get the pad. Okay. Please let me know if the screen is visible. I would need a voice cue for that.
Yes,
Sir?
it's visible.
Thank you. Thank you. Okay. Yeah. So till now we have been learning about fuse mode deposition. Okay. Let's just briefly go through what really happens in a, not in the process, but in a machine. Okay. So as you know that in this mode of deposition, there's a extruder. Okay. So there's a small nozzle through which metal filaments, not metal filaments, rather polymer filaments are actually put on. Okay, so what happens is that there's a small set of gears which gently push over the wire. Okay, this is the filament. All right, this is the filament, fibrous filament polymer. Okay, now because of friction exerting normal pressure on it, the rotation of these gears of one of them, of course, extrudes this filament into the nozzle. Okay, it pressurizes. But the problem is, because it is still solid, it would not go through until unless a lot of pressure is implemented. So what they do is they put some heating element over here. Right? I believe you already know this stuff. Okay. So we have a heating coil right about it. And then we have a motor on top of which the gear is connected. Okay. So that's one motor, one heating element. All right. This whole system, this entire system again is then moved in X, Y, and Z directions, isn't it? Now, how exactly this phenomenon is done? Imagine this is the extruder that I'm talking about. Okay, this is the extruder that I'm talking about. So what I'll do is I'll fix it over a platform. Okay, and this platform will be clamped to a belt, a straight linear belt. Okay, and this belt will come across with a, all right, which is again then connected to the motor. All right, so I'll have a complete circular belt. So this blocks is nothing but the extruder assembly. All right, so we'll have a belt which is teethed in nature. And you can very well imagine that as we move the motor, okay, this particular motor, there will be a displacement in x-axis. Okay, and hence this motor is called an X-stage motor. These are called stages. So that's an X-stage motor. Now what happens is that as this object moves, you will see in any 3D printing machine, you will see that there's a small switch, not like the switch in our houses, but there's a small lever, roller-like lever, and there's a small relay. So what happens is that as this extruder comes to the extreme point, this roller gets actuated, it gets displaced, and it trips a circuit. Okay, it switches off a circuit. What does it mean? That it has come to the final perimeter of the body. Okay, so this belt will make a full rotation about another gear where we need not put a motor because one motor is sufficient. Okay, a similar thing now happens on the Y stage. There's a motor, there's a cross belt. Okay, likewise, and you get an X and Y motion by controlling the X stage motor and the Y stage motor. Okay, that's X and Y. The whole platform on which these X and Y motors are staged, okay, is housed on top of a lead screw. I hope you have come across lead screw. Okay, what's a lead screw? It's a straight shaft with an axial pitch. Okay, and on top of this lead screw we have a small nut, all right, which undergoes linear displacement and is connected to this whole stage of X and Y. This is nothing but a Z stage. The motor over here is directly connected to the Z stage. Now you will wonder how the specifications of this particular motor change. Okay, just think about it. The pitch of the lead screw decides the thickness at which printing is done. Because for one revolution of the motor, it is going at 1 mm. All right, say for one revolution of the motor. Okay, so for 0.5 revolutions, we are going to get 0.5 mm. So based upon this pitch, if there is no resolution between 0.5 and 1, we cannot print parts at 0.75 or 0.8 or 0.9 accuracy. Okay, so the pitch has to be really refined, and this actually determines the thickness of the layer that the machine can produce. I'm sure you have already come across the effect of layer height, okay, which causes the staircase effect, right? If you are making a slant part, if your thickness is pretty high, you are going to get this staircase effect. All right, if your thickness is low, you're going to get it really refined. All right, so this is how it works. So that's about the FDM machine. Okay, now what are the systems here? We have a X stage motor, we have a Y stage motor, we have a Z stage motor, we have a heating element, and also we have a extruder motor, isn't it? So these are the four components, and on top of which some of the FDM machines also have a heated bed. That is very important to get rid of what? Do you know why a heated bed is required for printing? Any idea? You can type it in the chat box. Why do we need a heated bed? Any idea regarding this? Why do we need a heated bed? You can speak up, no problem. If you don't know, I'll explain. So that layers can join. Okay. All right. Okay. I'll give you an example. What if there's no heated bed? Okay. So imagine that this is the bed on top of which the printing has been carried out. Okay. And this is not heated. Okay. The extruder has deposited the first layer. All right. So where do you think maximum cooling will take place? Not by convection, but by conduction, isn't it? So the maximum cooling takes place beneath the table if it is not heated. Now what happens is that because there's a sequential cooling, and you will add another layer which is at higher temperature than the previous layer. Okay, so all the cooling will be done over this part only. Consequently, what happened, there's something called as thermal stress. Okay, that starts to build up, and because of which this part will start to shrink because there is no uniform cooling in the system. And what you will get at the end is a part shaped like this. If you search on Google warping of 3D printed parts, you'll be surprised how without a heated bed the parts get absolutely destroyed. Okay, but there's a small condition also. If your part is so small that the deformation is almost non-existent, then it really does not matter. So what do we know from here? We know from here that if we do not have a heated bed 3D printer, we will like to orient our parts in such a way that it does not fall flat on the bottom surface. Is this concept clear? How will we counter this problem? By keeping the bed contact area as low as possible. We might need to create more supports. We might need more printing time, but additionally, we have to go to this particular orientation so that our parts do not get damaged. Okay, just for example, if I want to print the Empire State Building, the model of Empire State Building without a heated bed, this will not be the best orientation. What will be the best orientation? This will be the best orientation. Of course, you will need a lot of supports to 3D print this. I hope this particular concept is clear. Heated bed. Okay. So if you're buying a DIY printer for yourself, which is of course fun activity now, this costs around 15-20,000, make sure you have a heated bed. Otherwise, you'll end up spending a lot on these supports which are useless and will of course damage the surface texture. Okay. So in an FDM machine, what we end up having, we have to control the speed of the motor of the extruder. That is control number 1. We have to control how X and Y stages are done. Now these are geometry based, isn't it? Geometry based, right? Z stage is layer height based. Layer height based. And eventually, heating element is operation based. Okay, at what speed do you need? If you increase the feed rate, if you move it really fast, you would need a really good amount of heating. So that sufficient element comes through. If your extruder is very fast and you are unable to deposit at that exact pace, what you will see that the layers will have some breakage in between. Okay, so the temperature of the heating element needs to be really high. Okay, so before we start the FDM process, there's always some certain conditioning that needs to be done. What? We need to set the extruder temperature. Okay, roughly to about 180 to 210 degrees Celsius. That is for PLA materials. There's also ABS. Okay, extruder temperature. Then we need to set the bed temperature to roughly about 65 degrees Celsius. Okay, so these are the what do you call it, preconditioning that needs to be done in an FDM process in order to eliminate structural damages while printing. I hope the working of a 3D printer in FDM is clear. Of course, you have already come across it. All right. Now, actually, my point was to take you to the SLA printing, the laser-based printing. Okay. So SLA really is not an acronym. It simply stands for stereolithography. Okay. And maybe you can add an apparatus at the end, and hence it might be called stereolithography apparatus, in short, SLA. SLA and SLS are to an extent very similar concepts, but they vary fundamentally with the process. Okay, so if you go through any rapid manufacturing textbook, you will see a lot of designations here and there and there. But what I really want to talk about is how these machines work. Maybe once you know how it works, it will not be as complicated to understand what its limitation might be. Okay. All right. So here, primarily, we are talking about lasers now. All right. This itself is again an acronym. Now, whenever we are operating with lasers, one thing we really are sure of is that we can work on a really small area. Because these lasers have a really fine resolution, these printers come with a very high resolution of surface image textures. Okay, the surface finish is absolutely smooth, and you can get micron layer thickness. The one in mechanical engineering department has, I believe, 80 micron to 160 micron range. Okay, so micrometer level of accuracy. So how is this laser capable of producing a 3D print? Now, the second concept is the resin that is used. Okay, the resin has a certain amount of photo inhibitors. What is photo inhibitors? Photo inhibitors are that part of a polymer chain which absorbs the energy from electromagnetic radiation and converts it into thermal energy, thereby solidifying the liquid. Okay, these are resin based. All right. So is it limited to resin only? No, we also have metal based laser printers. You can have a high power metal and melt two molecules of metal, not molecules of metal, two grains of metal, and fuse them together to form one single part. Okay, these are SLA based machines. Now, one thing we understand that we need to control the lasers, of course, the intensity of it, and the switching on and switching off the laser. Where exactly do you want to print? That is control parameter number one. The problem with SLA and SLS machine is that the raw material comes at high cost. Of course, you are going to get very good finish, but they also come at a really high cost, because the chemical equilibrium of the system has to be very homogeneous sort. I mean, homogeneous in the sense it cannot vary within the volume much. Otherwise, it will significantly affect your parts. One more thing to note about SLA system is that once the resin gets solidified, it's still rubbery-like. Okay, then you have to put it in another set of arrangement where photo curing takes place. What happens in photo curing? Again, you are going to give another beam of light, another wavelength of light, which is going to further solidify and strengthen the structure. Okay, but they have immense capacity in terms that you can, the assemblies that I was talking about is that you can through and through build down assemblies. Okay, and in SLS, the selective laser sintering process, which mostly deals with metals, you also have no need of creating supports, thereby getting a perfect surface texture as per requirement. Okay, any questions till here? Even in FDM, any questions? None? All right, no problem. You can come up later, maybe tomorrow. It's fine. Okay, so what happens in an SLA? Let's talk about how the laser is controlled. Okay, I'm sure you have heard something called as a galvanometer. Okay, so what is it? What's a galvanometer? Any idea? People? What's a galvanometer? And any idea what a galvanometer has to do with 3D printing? Anybody there? What's a galvanometer?
So it's an instrument to detect the electric current flow.
Correct. Very good. Simple. I believe most of you know about it. So what happens is that of some electrical arrangement, let's not go into it, we see a needle that deflects about certain angles because of flow of current. Okay. So how this can be used in 3D printing processes. Now this was very ingenious. You will notice that by little fluctuation of current, you can rapidly move this needle to and fro. That was evident. If you remember, the galvanometric metric uh, readings were not very stable. They used to flicker to a great extent, right? Then we have to tone it down. So if we really want high sensitivity, what is done is, instead of this needle, on the axis of the galvanometer, I'll place a small mirror. Okay. Now how will this mirror react? As this needle connected to all the coils and everything of the galvanometer, okay, will deflect with some angle theta, this mirror will also move, isn't it? So what happens is, if you have a source of laser pointing towards a mirror, okay, and you have this resin on which the laser is getting absorbed. If I deflect this mirror using a galvanometer, I can change the orientation of the laser, isn't it? Okay. Now, what's the consequence? I can deflect this laser to a large range, right? And then do whatever X motion I require. Okay. A pair of these, if I have two of them, each facing at 45 degree, and another one facing, say, me, this particular hits over here, this hits over here. Now I can deflect this laser here, as well as I can deflect the laser that is coming towards me. So if I have a resin in between, okay, I can create the X as well as the Y motion. Motion of what? The laser. By this, can you think about the concept that I'm not moving the laser head? It is static. All I'm doing is moving the mirrors. Now these mirrors are silver based, and a very thin film of silver is used, extremely light, have no inertia, which means that they are so precise and so easy to control by the sheer controlling of current and nothing else. You change the current level by microamperes, you get a deflection resolution of around 0.003 degrees, something like that. So if you can kind of understand how surface texture is now relevant to this, is because I can move the laser so precisely within the system that the surface roughness or the staircase effect in printing is almost negligible. Okay, that's an important point, and this is an advantage of the SLA process. Here, however, the power of the laser is in fact also very low. It's around 40 watt or 10 watt to 40 watt, not even very high, because we are working on resins over here. But the real challenge is not in this part. The real challenge is, how do you print layer by layer? Okay, and usually there are two approaches, a top-down approach and a bottoms-up approach, which means that an object, if say this is a triangle or a pyramid that I'm supposed to print on a 3D printer here, the conventional technique would be you point the mirrors of the laser in such a way that this printing takes place layer by layer, and what you do, the tray on which the resin is kept, you bring it down sequentially and replenish the top layer with resin. Okay, that is one way. The other way is you invert the object. Sorry. you invert the object and you start printing from bottom layer. Okay, and then you bring this stage uh, downward. Sorry, this stage goes upward. All right. So what is the first layer that you will see is the base layer, and on top of which sequentially these layers are going to get built. Okay, simply by deflection of mirrors, and hence you will often find the use of galvanometers, galvanometric or galvano in short, quite prominently in SLA based systems where lasers are used. Okay, now can you think of any advantage of printing it downward? Can you think of any how to print it downward, or what might be the advantage? Any idea? That should be totally intuition based. If I print anything downwards, what is that added advantage do I get? Or rather, also that might be a disadvantage. Okay, I'll put this to you. Maybe tomorrow, if we have a session, I'll definitely ask this. Okay, please go and search. What is the advantage of printing it upward and downward? All right. Okay, let's continue. So both type of SLAs are available. The one we have in the mechanical engineering department is from Formlabs. Okay, and I would say the speed of manufacturing a 3D printed part is almost same to that of a FDM machine. It's very comparable. Only the real difference is that one cannot compare the surface textures of both. Okay, just SLA is beyond any comparison. Okay, so this was SLA, a brief overview. We'll go into some presentations, see some pictures, how this laser is moving and things like that. But I want to give you a systems feel, where you know what a system is going through, what it is experiencing, and how things are working. Now, just thinking about it, what sort of displacement system do we require over here? There's one Z stage, two galvanometers that needs to be controlled. Okay, and what? Laser switching on and off. All right, these are the things that needs to be controlled while using this SLA and SLS type machines. Okay, coming to SLS, or selective laser sintering, which means that sintering is actually a standard mechanical process where powdered metal is used. Okay, so right there we have a challenge, that how exactly are you going to make the powder. It's a bigger challenge, because there was a sintering process already available. The powder technology is pretty advanced. Okay, so we need not worry about that. There's powder available, of course, at a very high cost, of any material that you want. The latest being titanium is being 3D printed, so that's a game changer for any industry. Now with SLS, the sintering process, the powder metal, what we do is use the laser, use a high power laser, melt the powder components, and then join them into one. That is the whole process. But there's a catch to it. What is the catch exactly? Let's go ahead and see. As you build the first layer, okay, you need to replenish the top layer with another layer of metal powder. And it doesn't matter what's the size of the object, you will have to replenish the entire surface, isn't it? So one good thing about SLS printer is that the time taken to print one object is independent except for the height parameter. Of course, if you make 1 meter tall object, it will take a lot of time compared to 1 centimeter object. Okay, height is a parameter, but then again, the number of components which needs to be printed really doesn't have any limitation. Okay, uh, so is this uh, oh, I missed one term which is very important. The movement of laser is actually called a scanning system. Okay, so that because the galvanometers are so fast, they are so responsive, the scanning is actually pretty fast. You really don't have to worry. It goes around I believe 50 meters per second or something like that. It's very fast. Okay, so the most applicable area I have seen of SLS, or it might not be metal, it could be any ceramic or things like that, is dentistry. So there are a lot of uh, dental houses, dental clinics. Now, I'm not sure if it is available in Northeast, but if you go to the rest of the India, what they will do is they'll make a mold of your teeth and everything. But what instead of hand carving it, they are going to 3D print it. Okay, by some ceramic. Now, there's some fundamental advantages that you get if you 3D. One, you can make the whole teeth hollow. You can just print the layers on top of it. Okay, but that seems pretty doable. However, if you do it manually, you will end up removing a lot of material from the teeth. Okay, so nowadays those 3D printed customized teeth implants are really in the market. Okay, you can get yourself done, but it has to be in batches. I was talking about filling up the material with powder. The problem with it is that not only that you have to fill the section with all the metal powder very homogeneously, you'll also have to maintain that precise layer thickness, which is pretty difficult to do so. Okay, in SLS, powder-based 3D printers. We'll see some pictures, we'll see some videos, it will be clearer. But if you understand what the challenge might be, if you have an intuition while looking at the machine video, you will realize it that, okay, I can get an idea what's happening, right? So if I, stack layer by layer by layer, a lot of volume of powder will be filled up by the time I have completed the whole print. Of course, the powder is reusable, but then again, you need that amount of powder. Say you're printing, imagine with gold, you want to make a small ornament out of it, but you have to fill the entire casing with gold, which is not advisable, isn't it? But think about this process. What if I want to make composites out of it? So I'll have an X stage roller. I'll also have a Y stage roller, having an entirely different amount of, different material. Okay. So after every 2 layer of X material, I can put every 1 layer of Y material. The laser that you're using is basically same. All right. Now with FDM processes, this was a little difficult, and with even resin also, it will be difficult because 2 resins will mix up chemically as well as physically. But because these are powders, they will not mix chemically and physically unless heated upon. But after heating is what you require. So this has a significant advantage of making alloys and composites. Okay, by sheer workflow of the system, we are trying to gauge some advantages and disadvantages out of it. Also, the third biggest advantage is that because we are filling the system with layers of powder over and over again, we do not need any support structures for the SLS types. Okay, one of the biggest advantages. Why? Because if you get rid of support structures, you essentially are ensuring perfect surface recreation of the 3D printed object. More so if you remember that robot that we were building, had a screw in between, if you remember, in the hole, which was larger. So if it starts printing layer wise, what will happen is that it will not create any supports in between over here. It will just fill it up with powder. Okay. And after it has printed all of it, if you remove this part, you can just empty the powder and it will be, this part will be free to move. So if you know that there's something called as a spherical joint, okay? So there's a cup in which there's a ball, and this ball is connected to one shaft. This cup is connected to one shaft. That's a sphere within a hollow sphere, okay? This sort of assemblies can be directly made because these are permanent assemblies. You cannot, make them unless you have fabricated over them. Okay, it's not possible. So these sort of assemblies can be right away made in SLS sort of a machine. Okay, so anything till here? Any information?
Juan, regarding the movement of the rollers you talked about in the X
Yeah.
direction and Y direction, how, if the layer thickness is so less, then how will it be different from, mixing the two powders and then rolling it at one go?
Yes, actually, what's for any chemical mixing to take place, the mixing has to happen at molecular level. Okay, here we are talking about micrometers, so which means that essentially we'll have 60 to 70 layers of one single powder particle. So 60 to 70 layer of one single powder particle will have literally no effect on the different layers that has to be compensated.
Okay.
Okay. Devraj has a point to make. To me, in SLS method, there seems to be no apparent advantage or disadvantage to the relative orientation of the printed object, as there is no question of supports. In SLA, the support factor has to be considered. Yes, that's absolutely correct. Inverting the design does not affect SLS, so that's one less thing to think about. Okay, but in SLA, I'm specifically mentioning SLA. What's the advantage? Okay, please do check, because these are the curiosities that you should have while understanding 3D printing. And maybe at some point, these inventions just came up randomly across the world at certain stages. There were not one research after another, so you never know how these inventions can come up. Okay, we have already pushed, I believe, around. So there's last 15 minutes. So should I interact or should I go ahead with content?
Interaction can be done with, active participants.
Right.
Dormant.
And I believe they are drained with so many concepts, SolidWorks plus this and that.
But anyway,
okay.
Tomorrow I expect some kind of active participation from all the students, and this will come if you study little bit about these things. So
yeah, I believe Google will be sufficient. Yeah.
They will not Google, I know them. So Juan, if you have some kind of materials, maybe documents or whatever, you are free to share in our WhatsApp group.
Okay.
Already there. So even some good website. I found some websites where all the methods were summarized. So that kind of websites can be shared. So one reading will be sufficient to trigger some kind of doubts.
Yes, it's mostly figure based, and I believe they have already seen a lot of videos.
Yes.
Yeah, so they will be able to catch pretty quickly. Until one dwells in building a machine, there's not quite that amount of information regarding 3D printing. Okay, that's all about how you intuitively arrange systems. Then again, let me take 5 minutes and talk about something that's very recent, current, and if you work on it, perhaps all you need is a computer to do so. So I believe everybody knows about artificial intelligence and machine learning. So in 3D printing, as you saw, I mentioned about 4 or 5 components, X, Y, extruder, heating element, galvanometers, this and that. So each of those systems have further subsystems, because the galvanometer will be an arrangement of motor coil parameters. So they will have their own response structure. Okay. Then the frame on which it is sitting, they'll have inherent vibrations and whatnot. What happens in due course of time is that only an experienced person can, give one good print in one single go. Okay, if you sit on a 3D printer today, I can assure you, you'll take multiple takes to get your first assembly ready, because a lot of problems even I have faced across, which seemed absolutely, um, unpredictable. It shouldn't have happened, absolutely, but they did. So what's happening is that, you start uploading this 3D CAD models into a cloud-based server, and if you give the company to print it, I forgot the name. So what they do is that not only they'll print it for you, they'll gather a lot of information about that particular part. With all that part, they are developing an AI model, a machine learned model, which automatically suggests the best orientation which is feasible. Now, if you will load your solid model in that open source software, I forgot the name, which exactly one that you are using for this course? I forgot. I believe it was Unimax or something like that. So they give you a by default orientation, which might not be true because you eventually toggle with it, right? But what's going to happen now is that your intuition, and the experience of learned personals will eventually be fit into this AI algorithm, and then this is used in building huge structures. One of the very fine projects that I know about is 3D printing in uh, underwater surfaces. So that's something really new, because Microsoft actually decided to, reduce their cooling load and the cost associated to cooling load by putting their servers on the ocean floor. Ocean floor is much cooler. Now the structures over there has to be mechanically built. Okay, that's a real problem. Now what they are doing is they are creating some uh, hydro 3D printers which land or on the surface floor, and they start building with the sand itself. Okay, so that's something very interesting with perspective to civil engineering, I believe, because there are so many currents, underneath currents, and concepts of structures that come up while assembling some beneath the ocean 3D printed objects. These things you can look in for how to develop some algorithms and stuff like that. All right. So I believe if you not have any more questions, we can close the session and then further continue tomorrow with some nice videos and lectures. I'll anyway supply. All right. So if you have any, I'm here. Otherwise, we can perhaps close the session. Over to you, Bibhuti.
Yes. So students, do you have any question, or should we wrap up? So silence will be taken as a yes for wrapping up this session, and thank you, Juan, for giving your time. Tomorrow we'll meet again at 5. Is it okay for you?
Yeah, sure, no problem. Tomorrow.
All right. So yeah, thank you.
Okay. Thank you, everyone.